from National University. So we are going to spend the rest of the afternoon lessons dealing with congruence and similarity. So with this regard, your cooperation will be highly appreciated. Now, I would just like to start by perhaps, and under the transformations, you should have done the transformation in the inner grades. Can you give some examples of the inner transformation that you do? We have enlightenment. We have the reflection. Now, or we have stretch position. We said we have to reflect those things we have done in the lower grades. We have rotation. We have the translation. Okay. What we are talking about the enlargement. What are the properties of an enlargement? To say that the figure has been enlarged. Or what are the properties that can come into management? You must know the use of the lines. We have the center of enlargement. Other than the center, what else do we have? We have the scale factor. The scale factor. What else? That's all you know about the what is the scale factor? The scale factor. How can you find the scale factor? Remember, we have the certain formula that we can. If I can denote the scale factor with the letter K, we are going to say the scale factor is given as image length over the object length. Now, it should be clear when, if I can just, this drawing or this figure is not to scale. We have 4 here, and then, let me just, it's 2 here. And then here it's 4 meters. And then say, now we have two figures. Suppose they are rectangles, we name them rectangles, and then it has to be here in your mind when you are talking about the alignment. If you want to find the scale factor, I think this is just a reminder because we've done them in your work. So how do you find the scale factor? Okay. Suppose figure B is enlargement of figure A. After you have enlarged figure A using a certain scale factor. The point is I want us to find the scale factor. How can we find the scale factor in this regard? Because we say the scale factor is given by this formula, the image length over the object length. So this time around we are going to take our figure A as our object, and this one is going to be our image. Now,
find, we'll say 4 meters divided by 8 meters, and 1 meter divided by 2 meters.
He said we can have our scale factor given as 8 meters divided by 4 meters.
No, 4 meters divided by
4 meters divided by 8 meters. I said you enlarge this figure, or this figure is transformed using a certain scale factor. So it has to be clear as what the question said. You have to make sure that you understand the question. Because we can have a fractional scale factor, of which you are sure that the image is going to be smaller than the object. In a case where we have say a scale factor greater than 1, in that case you are sure that your object, your image is going to be greater than your object. Are you okay with that?
Yes.
Okay. Now you transform this figure using a certain scale factor. You are given all the size of both the object and the image. Maybe to avoid confusion, say this one is the image and then this one is the object. You want to correct this?
Yes, sir. 4 meters divided by 8 meters.
So we are going to have 4 over 8. So which is so this is an example of a fractional scale factor. We are not going to go into much detail into this. But I just wanted to show that if we are talking about an enlargement, that's one of our transformations, we can have a different shape from a different image from the object. But there can be a case whereby the image is the same as the object. Can you think of a case whereby we can have the image and the object being exactly the same but still using enlargement? In that case, what will be our scale factor? Can you think of a situation whereby we are going to have the object, we transform it using a certain scale factor, and then after transforming that figure or that object, we still get the same object. We are not going to alter the shape of the object. Now,
Scale factor will be 1.
in that case, the scale factor will be 1, and it's very difficult, or it's not easy. Let me say, it's not easy to recognize that unless you are told. But since I said the focus of the lesson today, we shall be talking about the congruence and similarity. So it is very important. So here, when you come to reflection, are there any questions before I can go to reflection? Are there any questions on analyzing? So when we are coming to rotation, even these 3 types of transformations, we have the reflection, the rotation, and the translations. Will we have any difference with regard to the shape, with respect to both object and the image? They are going to be the same. Is that the case? Okay. Now, I said our focus today is going to be congruence and similarity. Congruence and similarity. Now, when we say 2 figures or 2 shapes are congruent, we mean they are exactly the same. In other words, they are equal. Meaning the shape and the size are exactly the same. Is everybody happy? Okay. If you are happy with the explanation, then we are going to focus on congruence in the first part of this lesson. And then we will see that there are certain postulates or the theorems or the properties of congruence figures. But there can be some real life examples when we are talking about congruence. Our explanation, we say by congruence we mean that a figure or a shape or two shapes or two figures are exactly the same with regard to size and, we mentioned size and shape. So my earlier question was, can you think of a real life example of congruent figures or anything that you can say is congruent? Still bearing in mind that the mathematical language is somehow different from the everyday language that we use. Because I talked about equality. When I'm talking about congruence, I say they are equal, exactly the same. Exactly the same. Maybe that is the everyday English. That is. When it comes to people, anybody? Yeah.
Identical twins.
We can have identical twins. We can have an example of identical twins. That's where the idea or the concept of congruence can come in everyday life. Any other example that you can think of other than identical twins? Are you going to say congruent twins? It's only identical because that is English. Everyday English. Any other example that you can think of? Looking at yourself in the mirror. That is the concept of reflection. How about matchbox? Are they identical? So like I said, we are going to base ourselves on the concept of congruence. Congruence and similarity. Now, I said there are four basic properties of congruence. Maybe for simplicity we are going to be basing ourselves on the triangles. When we are talking about the triangles, we are going to compare two triangles. Suppose we have triangle A. We have triangle A and triangle B. Now, looking at these two triangles, suppose this length, we are going to be measuring this length basing ourselves on the correspondence. So we are going to say corresponding side. So this side actually corresponds to this one. So when you look at your two figures or two triangles, this one is the same as this one. We are going to say the two corresponding sides of these two triangles are equal. Again, we can say this length is also equal to this length. Again, this one. So what we have to bear in mind here is that the orientation doesn't matter in this case. It doesn't how these two are placed by, as long as you can see the corresponding sides. So all the corresponding sides of these two triangles are equal, meaning this length is equal to this one. So we are going to say the three sides are corresponding. So the criteria or the postulate that we are going to use, we say side. Let me just denote the side by the letter F. So this is the first postulate. If we are given the two triangles, triangle A and triangle B, you just check if all the corresponding sides of triangle A are equal to those in triangle B. Is this example clear? Okay. Now, let me go to postulate number 2. We may have another triangle here. This time around I'm going to name the same orientation. Appropriate is 2 meters. 2 meters. Now, when you look at these two triangles, the corresponding sides are equal. And this angle, which is sandwiched between the two lengths, is also equal with regard to both triangles. This interior angle is the same, or it is equal. And the two corresponding sides are also equal. So in that case, we are going to say we have corresponding sides. The first corresponding side is equal, and then we have the angle sandwiched between the two sides. So this is the second. This is the second postulate of congruence. In that case, you can say the two triangles are congruent. Any question up to this? Is everything clear up to you? Now, we have different types of triangles, and it doesn't matter which type of triangle we are going to be using ourselves on, as long as we can see that the corresponding sides are equal, and then you have to be able, because sometimes can be asked to give reasons. Why are you saying that the two triangles are? What has to come into our mind is the postulate that we are going to do, or the two that we have done so far. I talked about the different types of triangles, which I gave you just take this in mind. Types of triangles. Any type of triangle that you want. We have done them since standard 7. We have by isosceles triangle. What is an isosceles triangle? How can you do that? This one is an isosceles triangle. Definition of isosceles triangle. Isosceles triangle.
It's a triangle where only two sides are.
The triangle whereby two sides are equal. We refer to it as isosceles triangle. Any other type of triangle that you know? Scalene triangle. Definition of a scalene triangle. All the three sides are not equal or are different. Another type. talked about the isosceles, the scaling. Still have two more. Equilateral triangle. So what is an equilateral triangle? An equilateral triangle. An equilateral triangle. All the three sides of that triangle are equal. One more. I saw many people saying that I don't. We still have one more. We talked about the scaling triangle, isosceles triangle, and the equilateral triangle. Whereby we say the isosceles triangle, the one which has two sides. The scaling, all the three sides are different. And the equilateral triangle, all the three sides of the triangle are equal. One more. Are you aware that some of you are raising up their hands, meaning there is still the fourth one? What is the fourth triangle? There is nothing like that. Remember when we were talking about the Pythagoras rule or Pythagoras theorem? When we were talking about the Pythagoras theorem, that's an angle, not a triangle. Okay, what was he saying to you?
He mentioned a right angled triangle.
Right angled triangle. Is there another type here?
Yes.
Can we talk about an isosceles triangle when we are dealing with Pythagoras theorem?
No.
How about the equilateral triangle? There's nothing like that. So when we are talking about the Pythagoras theorem, what we have? We have a right angled triangle. A right angled triangle. What is a right angled triangle? How can you see that this one is a right angled triangle? Not that way.
An angle in which one of the angles equals to 90 degrees.
One of its interior angles is equal to 90 degrees, or it's a right angle. So this will prompt me to talk about the interior angles of a triangle, the sum of the interior angles. So if you are given a right angle triangle, you know for sure that here is 90 degrees. So suppose you have angle X and angle Y. You can only find, if you are given the two interior angles, you can find the third one using, you should be able to know the angle sum of a triangle. What is the angle sum? 180 degrees. Is it not degrees Celsius? Because there has been some misconceptions, because in science they talk about degrees Celsius. So when we are having an exam, you start to just say it's 180 because we are used to Celsius and you say Celsius. This is temperature again. Make sure not going to make that mistake. Are there any questions up to this far?
I'll say, as a right angle triangle, is it necessary? Is it one of the types?
Yeah, because when you're talking about the Pythagoras theorem, we forget about the scaling, we talked about. It's true that maybe it can be a subset of one of those that we have mentioned. It can be, but personally I regard it as another type of of the frequency of a triangle. Any other question with regard to what we've done up to this? There is no question. Meaning everything is clear. We talked about the congruence, the first two postulates of congruence. Now I'm just going to stop here, and then my colleague here will just go on with the rest of the two postulates.
Afternoon, everybody. Do we exactly understand everything here? What can anyone say about congruence? Why do we consider congruence in triangles? Okay, while you are thinking, what if I were to say this length, like this length, is not equal to this length? Will these two figures be equal? Be congruent? Why? Why? Because the corresponding sides are not equal. What if this angle of view from this side to this side, and then you get this one here? Will these two triangles be congruent?
Yes.
Can you share this with somebody beside you? You only change the triangle. Suppose you are not given this triangle, you are given this one, and here you are given this one. Well, these two figures be congruent. Share this.
Just showing the other than
conclusion is that two triangles are not one.
Because you're not certainly sure that this angle is here. Because if this
What if somebody said, because here we have 30 degrees, and here we have 30 degrees?
that would be cool. Oh, and here we have 30 degrees and here 30 degrees.
But we have to make sure that which postulate are you using, which will allow you to say these two triangles are equal. The postulate that we have discussed is true that we have only discussed only to find
The one for is angle length.
These are the only two.
So with this equal to this, can they continue? None of them is. Meaning this triangle is not congruent. So this is how we remove the symbol for congrunce. This one is triangle A is congruent for triangle B. But if they are not congruent,
So in this case, some sense, or if it's said to it's not quite equal. And yes, to me they are something that
that's why the picture is congruent. So if the angle is now at a different point, not exactly the same, just in the other angle.
Remember, what is it when you say that is these two figures, their sides are but they are exactly the same.
We have an angle, we have this side, and this side together the same. Then we have another side with the same size and shape, but now the angle is here. Meaning that these two angles do not correspond.
These two angles are not necessarily the same. But that's not necessarily this angle is not so you can be given a certain angle, not exactly, not necessarily the same angle as the one for the condition of congruence. Condition says you should have SAS, right? So sometimes you can be given this angle, and then this one to apply the division of triangles, and then find this one. If you do that, you find that this angle is exactly the same as this one. So from this kind, the moment that these two figures are the same in terms of size and shape, you have to understand that no matter whether this angle is not given or any other two are given, and then you're supposed to find this one. These two figures are congruent.
So if they are the congruent, now we have the side, we have another side, but we have that our proof will be full.
Knowing how also.
Yes, I wouldn't disagree that this angles are equal, but we have the sides, the two sides, this one and this one. The two sides, they are equal. They give us the green light to the congruence of the sandwiches, but my problem is with this angle.
These angles are not necessarily the same. Of course, they are not the same. But what happens here is, you see, you cannot directly be given an angle which is between these two sides. You could be given rather two angles which through that we can calculate that angle which should be.
So we can use another formula of the hypotenuse or anything else.
Anything else? No, the summation of 180. That the summation of
So in most cases, if we are in this situation with the two sides that prove that this is congruent, we might find out that the triangle given is an isosceles, so that we can find the inner, so that we can.
So what I was trying to show you was not necessarily
the cases you will be given shapes which the same period and the same. Sometimes you'll be given these two numbers and this one. So you find that they are still the same. No,
That's what she thinks. I think this thing is important to this thing. Even though it's not given, this one is important to this thing.
what I was trying to bring into mind is that not in all the cases you will be given, in fact, not in all the cases you will realize that